Okay, good morning. Here's the joke of the day. Did you hear oxygen went on a date with potassium? It went okay. That's pretty medium. It's not as bad as the other one though. Today we're going to go over the homework. I did pick out one mistake that I made, so we'll hit that. We'll also go over your nuclear decay reactions that you had for homework. And today we're going to learn about half-lives. You're going to have homework for half-life, and tomorrow by 3:15 you will have the quiz that's due. I posted it yesterday. I will be open today at 2 for office hours. I think I already posted it, but I'll make sure. This lab is going to be due next Wednesday that I posted. You can use M&Ms, you can use Skittles, you can use pennies if you want. Okay? So let's look at the homework first. Which one do we have? I think it's this one. The mistake that I made, I think, was on this. We've got a beta emission here. I know it's beta emission because it is a -1. And let's remind ourselves what those are. Here's my CRT. Here are the alpha particles. Okay, it's like a helium atom. Beta particle, which is like a high-speed electron, no mass but a -1 charge. Just a reminder, gamma radiation, there's no mass or charge, but it does have very good penetration. It can do a lot of damage. We already know about neutrons and protons. And positron was the one we learned yesterday. Positrons are kind of the anti-electron in that they have the same mass, but they have a positive charge. Okay? So we're going to pull this down because we're going to look at that here in a second. So when I did this, I think I put 39. This number here was right. Whoops. This number here was right, but I put potassium. Potassium has a mass number of 39. It does not have an atomic number of 39. Atomic number 39 is yttrium. Okay? So the rest of these were correct, but I wanted to make note of that one. All right? Okay, so the other homework was this one. Now, I went ahead and to save some time, I went ahead and put down each of the emissions. So this one's alpha. Whoops. This one's alpha. Let's change colors here. These are all alpha emissions. So I put the helium atom each time. So remember, when we're doing these have to, both the mass and the atomic number have to be equal to what it starts with. All right? So using that information, I can just subtract. 82 plus 2 is 84. 210 minus 4 is 206. And then I'm going to do all the math and then go look all of them up. Okay? So 92 minus 2 is 90. 238 minus 4 is 234. 90 minus 2 is 88. 238 minus 4 is 234 again. And 86 minus 2 is 84. 222 minus 4 is 218. Okay, so then you would just look these up. Let's remember them first. 82, 84, 88, and 90. 82. Oh, I didn't want that one. I want this one. 82 is lead. 84 is polonium. Madame Curie discovered that one, remember? 84 and 90 is thorium, and 92 is uranium. See if we can remember that. 82 is lead. 84, I forgot already. 84 is polonium. 88 is thorium, I believe. Nope, that's 90. 88 is radium. And 90 is uranium. Take that back. 90 is thorium. Okay, so hopefully I got those right. All right? Lead, thorium, radium, and polonium. Okay? Next section. Beta decay. Remember, you would see beta decay as a -1 with an electron and 0. You might also see it as beta like this. Okay? So be prepared for that. So in this case, since I've got -1, it has to be 1 higher than what I've got here. Okay? So 7. Why? Because 7 plus a -1 is 6. There's no change here in the mass, so that's 14.7. So on this side, I need this number to be 1 higher than that. So there's 39 again, and the mass number is the same. 19 is 20, mass number is the same. 7 and 8, and mass number is the same. So I know some of these by the top of my head. 7 is nitrogen, 20 is calcium, and 8 is oxygen, and 39 we just did. I believe that's yttrium. 39 yttrium. Let's check. 39 yttrium. Okay, there it is. Okay. All right, last bit here. The following all undergo positron emission. Okay, remind ourselves what positrons look like. Positrons are kind of like anti-electrons. 0 mass, +1 charge. You might actually see it as a beta like that, +1, okay, with a beta sign, because it's really kind of the opposite of an electron. All right, so that's a positron, so you got to keep that in mind. So in this case, since these are positive, this number here has to be 1 less, 1 fewer than that one, because than what we started with. So this is 49. So 49 plus 1 is 50. No change in mass, so the top numbers are going to be the same all the way across. So 61, this must be 28. 28 plus 1 is 29. This is 1 fewer, that's 15, that stays the same. And 38, so this is 37. 37 plus 1 is 38, that number stays the same. That's a 7. All right. I know this one, that's phosphorus. The other ones I'm going to have to look up. 28, 37, 49. 28 is nickel. 37 is rubidium. And let's do those first. 28 is nickel. 37 is rubidium. 28 is nickel. 37 is rubidium. And the other one was 49. 49 is indium. I-N. Okay? So hopefully this isn't too bad for you. Okay? So you should be able to look these up, and then in the table N, I think it's N. Yep. In table N, you should be able to figure out what it becomes based on this. All right? But today, and we'll practice that right now actually, today we're going to be learning about half-lives. Okay? So, we just practiced some nuclear equations. You should be okay with that. You should be able to explain this. There's a question like that on your quiz. Why do the beta rays move further away than alpha rays? Because they have less mass, right? And the alpha rays are diverted to the negative plate because they're positively charged. The opposite's true of the beta rays. They're attracted to the positive because they're negatively charged. Gamma go right through because they have no charge on them at all. Okay? And Other than that, it's what kind of emission and what kind of energy, all right? So, let's look at half-life today. Half-life is defined as the amount of time required for 1/2 of a radioactive isotope to decay or disintegrate. The rate of decay is constant. It is fixed. That's why when we look at this, look at all these different units too. We've got seconds, hours, days, years, minutes. I think there's one that's milliseconds too. Milliseconds, right? So these are fixed. They decay at a constant rate. This is also different. The rate of decay is different for every isotope. Even within the same atom, the same kind of atom, I should say. Elements have different radioactive isotopes. Each of those isotopes has a different rate of decay. So let's see what happens here. If I have 20 grams of radium-226, its half-life is 1599. I'm just going to convert it to 1600 just for explaining purposes. What happens here? Well, let's practice a little bit first. So I've got 226 radium. Let's look up radium. Radium is Ra, so that's down here. It's a little hard to read. Radium is 88. That's 88. Now, it decays. What kind of decay does it go through? Well, let's look. Radium-226. There's your half-life. It goes through alpha emission. So, it's going to decay here. And by now you should know that an alpha is really just a helium atom. And now I can figure out what it decays into. This is 86. This is 222. And 88 into an 86. 86 is radon. Rn. Okay? So you should be able to do that with almost anything as long as it's on that table. Okay? Now, that's just practice. It doesn't have anything to do with the half-life part, except that you should know that this doesn't disappear when it says it's going through a half-life. The atoms are getting converted into something else. So in this case, they're converted into helium and into radon. All right? So as we go through these problems, keep that in mind. All right, back to this problem. If I have 20 grams of 226 radium, its half-life is 1599, we're going to call it 1600. What happens? So if we're at time 0, it's going to take 1600 years for the first half-life. So if I start with 20 grams, after 1600 years, I'm going to have 10 grams of the radioactive element of radium left. What about the other 10 grams? I've got 10 grams of this left. The rest is a combination of this. Okay? So what's going to be left there is the combination of helium and radon. So this is going to have some mass, but together these things will have a mass of 10 grams because I can't lose any mass. I start with 20, I still have to have 20 total. How about another 1600 years, 3200? So that's my second half-life. Now I'm ending with 5 grams of radium, and the total here has to be 15 grams. Why? Because this total has to equal this total. Okay? Another one, 2.5 grams. How much is going to be here? 17.5 grams. After 4 half-lives, 1.25 grams will still be the radioactive radium. How much will be helium and radon? Together it's going to be 18.75 grams. Okay, so we're not losing anything. That's something to keep in mind. There will always be some radioactive isotope left. 1.25, 0.625, 0.3625. You will continue to do that hypothetically until there are just there's one atom left. Okay, so hypothetically you would technically never get to 0 because it's always half until you get to that last atom, I suppose. Okay, so let's look at an example problem. Isotope of cesium-137. Here's the cesium. Now, we're doing this just for practice, so don't, this isn't really part of the problem. It's just a practice, just like we did over there. So cesium-137. Let's find cesium-137. There it is, 137, 30.2 years. It goes through a beta emission. Beta emission. And again, you don't have to, this is not part of this problem. I'm just showing you for practice. So beta is an electron with 0 and a -1. Let's look for cesium. Cesium is CS over here. Hard to read. It's not in focus very well. That is number 55. 55. So, what does this have to be? This has to be 56. This number does not change. So what's 56? That's a 5, by the way, sorry. What's 56? 56 is barium. So barium is the end product of cesium beta emission. Okay? So when this starts to break down, it gets converted into barium and then some beta. All right? So just showing you that. Just showing you that. All right, let's look at the problem now. Come on there. Anyway. Let's switch colors quick. Blue. Okay. So we start with, and this is really, I found that over the time, because I used to teach this in biology too, and you've already learned it in earth science, so it shouldn't be too bad. Isotope starts with half-life of 30 years if 1 milligram disintegrates over 90 years. So we're starting with 1 milligram. So I'm going to put 1 milligram here. I'm going to draw an arrow, and this is my sample, okay? Chunk of rock or whatever. And it takes 30 years for its half-life. So I'm going to draw the same size box, and I'm going to shade all this, indicating that it's all the radioactive. What's going to happen over 30 years? It's going to disintegrate into barium. That's what we just saw, right? So that's half of a milligram, 0.5. 0.5 milligrams. And the rest of this is going to be barium. Now, will 1/2 of this change? No. It's completely random which atoms disintegrate and then turn into the barium. So there's 30 years. They're asking for 90 years. So that's another 30 years. So I draw my same box, except I'm going to make it half as big as what that one shows. And what's half of 0.5? 0.25. And the rest is going to be barium, plus a little bit of electron from the beta. Okay? And I have to go another 30 years. Drawing the same box, half of this, so it's kind of like a sliver. And what's half of 0.25? 0.625. Nope, I did that wrong. It's 0.125. Get off of there. Sorry. Half of 25 is 12.5, so that's 0.125 grams. So, After 30 years, I have half. After another 30 years, I have half of what remains. After another 30 years, I have half of what remains. So I end up with 0.125 grams of cesium-137. Okay? We'll do this other one and then we'll be done. A 2.5 gram sample of isotope strontium-90 was formed in a 1960 explosion of an atomic bomb at Johnson Island in the Pacific Test Site. Early experiments of nuclear explosions were done in the Pacific, Bikini Island, and then they would test them afterwards. Not a lot of life going on there after such explosions. The half-life of strontium-90 is 28 years. In what year will 0.625 grams remain? Okay, so we're starting with 2.5. So 2.5 grams, and this is my strontium-90. I'm going to save a little time and not show you what it gets broken down into because we're running a little long. So all of this is 2.5 grams. Okay, half-life is 28 years. So in 28 years, what's going to happen? Half of this sample is going to be radioactive. What's half of 2.5? 1.25. Okay, I'm not at 0.625 yet, so I need another half-life. Same sample, half of that one. 0.625. Okay, so I'm left with 0.625 grams. Now they're asking what year. How long did it take me to go from here to here? I have to add these up. 28 plus 28 is 56 years. That's equals. If they started in 1960, that's when the explosion occurred. This is times 0. And then it took 2 half-lives. I have to add this together. This is 6, that's 11, that's a 2. So it would take until 2016 to have 0.625 grams left. Okay? So those are some examples. The homework that I want you to do is not that one, is this one, which is in the packet. Okay? Try these. There are 6 of them. Should take you maybe 15, 20 minutes. Okay? Good luck.